Good morning. Last lecture, we stopped at line-to-line voltages or phase-to-phase voltages. In summary, line-to-line voltages are when we put the positive at one phase and negative at the other phase without using the neutral. So when we do any line-to-line voltages, we will not use neutral at all. So V line-to-line will be between A to B, B to C, C to A. As we see here, like the positive can be at A, negative at B, or positive at B, negative at A, or positive at C, negative at A. As a result, now we have 6 voltages so far. What are these 6 voltages? We have 6 voltages. The first 3 voltages are line to neutral, and those are 3 voltages. What are these line to neutral voltages? Those are VAN, VBN, VCN. Those are line to neutral, which is there is a neutral on it, so we are using the neutral. And there are line-to-line voltages, and those are 3 as well. And line-to-line voltages, we will no longer use the neutral, so we will say VAB, VBC, VCA. Those again, line-to-line voltages. So whenever you see anything like 6 voltages, we mean 3 line-to-line, 3 line-to-neutral. So take it as a rule from now, 6 voltages, we mean by all of these 3. And regarding to the currents, we have 4 currents. What are these currents? We have IA, the current of each conductor, IB, IC, and I neutral. Most likely I neutral equal to 0 if and only if the system is balanced. If the system is unbalanced, then the neutral current is not 0. While otherwise, if we assume it is balanced, then the neutral current every time will be 0. Under a balanced situation, how to calculate VA and VAB, VBC, VCA, which is how to calculate line-to-line voltages. Those are the formula governing this. So VAB equal VAN minus VBN, VBC equal VBN minus VCN, VCA equal VCN minus VAN. These 3 formulas, keep in mind, those are valid true and valid anytime, even if the system is unbalanced. Even if the system is unbalanced. Therefore, I used to call these formulas as the general formulas. So general formulas, which is basically are valid every time. You don't need to worry if the system is balanced or unbalanced. Just VAB, VAB, the first letter A minus B. VBC, first letter B minus C. VCA, first letter C minus VA. That's how we know it. So you don't need actually to worry about how can I memorize this. VAB, VAN minus VBN, and so on for the others. Now, when you look at these formulas, you will see VAN minus VBN, which is 2 complex quantities and there's a negative sign, subtracting 2 negative quantities. This sometimes can take a lot of time. So as a result, we would like to see if there is any other formulas that we can conclude or we can find, or any shortcuts to calculate VAB, VBC, VCA, other than subtracting 2 complex quantities. Basically, if you want to do it in handwritten, it will take a long time. If you want to do it in the calculator, it will be faster. But is there any other faster method? The answer is yes. How? Or we can use some special cases, which is those are valid anytime, while we have a special case here. If the system is balanced, then we can say that we can get some special formulas. And as we know, the sequence can be either positive sequence or negative sequence, right? As we discussed last lecture, positive sequence or negative sequence, or in other words, ABC or CBA, or ACB, whatever. So for ABC, with angle 0, A, B, negative 120, C with positive 120. ACB is the opposite, 0. Just swap between C and B, so C will be negative 120, B will be with positive 120. So you need to be aware of all of these sequences. Then we will say, as a result, if the system is balanced and positive sequence, then we can calculate VAB by saying square root of 3 angle 30 degrees times VAN. So the first letter A times VAN. The second one, VBC, will be square root of 3 angle 30 times VBN, because the first letter of it B. Then the first letter of that one, VCA, is C, so times VCN, root 3 angle 30 degrees. Okay? So we see this formula, it can be, much easier than using VAN minus VBN. How? Because when we have a product of a complex numbers, we can say just multiply the magnitude with square root of 3 and the angle just add 30 degrees. That's it. That's how we can make it easy. Then when we look only again at the magnitude alone, VAB as a magnitude equals VBC as a magnitude, because it's balanced, equal VCA as a magnitude. Or in other words, this magnitude I'm going to call it as VLL, because they are all sharing the same magnitude. And it's going to be as square root of 3 times the magnitude, or VRMS. Or in other words, I would say V line to neutral. The RMS of line to neutral. Okay? Because I'm going to assume the magnitude of line to neutral, like VAN as a magnitude, equal VBN as a magnitude, equal VCN as a magnitude, and I'm going to call it as VLN. Without bars. Keep in mind, those are magnitude without bars, without the angles, so only the magnitude. So as a result, we get this famous formula that we will use it a lot. V line to line equals root 3 times V line to neutral. And again, what's the V line to line? Is the magnitude of all VAB, VBC, VCA. What's V line to neutral? The magnitude of VAN, VBN, VCN. Okay? So if the system is negative sequence, so that one, the first one was for positive sequence. If it is negative sequence, it will be the same for the magnitude, root of 3, but it will be with angle, negative angle. Negative angle. And the same way, VAB use VAN, VBC use VBN, VCA, first letter C, use VCN. Okay? Does this make sense? So these formulas, again, are true if the system is balanced, and there are formulas in the left-hand side for positive sequence, right-hand side of the negative sequence. And the formula that we got, V line to line equal root of 3 times V line to neutral, this is valid if it is positive sequence or negative sequence, because we see the magnitude, all of them multiplied by root 3, all of them multiplied by root 3. So they are all the same magnitude. The difference with the sequence is the angle. If positive sequence, positive 30, negative sequence, negative 30. Just like from the name of the sequence. If it's positive, positive angle. Negative, negative angle. Again, these formulas, what I would say, these formulas not always true. Not always true. Those are not always true. So there will be some conditions. When will this formula will be true? If and only if balanced. If and only if balanced. If the system is unbalanced, what should I do? Don't use this. Okay, what should I use? Use the general equations, which is this. Okay? Somebody can say, okay, since the general formula is valid anytime, I don't want to use this formula. I want to use the general formula anytime. It's up to you. There is no problem. But the thing which is, this might take longer time, but it might not be too long. But just for your information, that's the general formula, and we have special cases. So I will say those can be considered as special cases. Then again, it's very important. If the system is unbalanced, don't use those. So what should I do? Use general formula. Okay? Which is again, general formulas mean VAB equal VAN minus VBN. Then the same thing when we do for VBC and VCA. So you should know this. Okay? So far we have 6 voltages. 3 line to line, 3 line to neutral. The magnitude of line to line, we used to call it VLN. The magnitude of V line to neutral, we used to call it VLL. The relationship between line to line and line to neutral, if the system is balanced, we will say V line to line equals square root of 3 times V line to neutral as a magnitude. While as the angle, we know like square root of 3 angle 30 or square root of 3 angle negative 30 if it is positive or negative sequence. If the system is unbalanced, use the general formula. And again, unbalanced means different in angle, different in magnitude, or in both. Okay. So as a standard, to standardize our analysis, every time we will assume phase A as a reference. So we will pick the voltage VAN always as with angle 0 degrees. If you have the choice to make this assumption. If it is given to you, don't assume it as 0. Assume what's given to you. So that's if you have the choice to do the analysis or to choose the angle of phase A, then choose it. If sometimes it can be given, just use what you have. Okay? Then the second thing, every time, whenever you see any voltage value, it is line to line. It's not line to neutral. So what does this mean and what should I do? When you read any label of a motor or 3-phase motor or any label of any 3-phase device, that's voltage. It will not tell you this is V line to line, this is V line to neutral. It will say, for example, 12.47 kilovolts 3-phase induction motor, something like that. So what does this value mean? It's 3-phase. So is this line to line or line to neutral? The default, if there is no information about it, if there is no indication says this is V line to line or this is V line to neutral, the default, this is V line to line. Okay? So when we see any label says V line to line equal to this value. So what we need to do is, we used to say, for example, a system has 500 kilovolts without mentioning anything. So you will say V line to line equals 500 kilovolts. Then what should I do? You will say V line to neutral equal V line to line over square root of 3. After that, you will say that VAN equals V line to neutral angle 0 degrees, which is, in other words, 500 kilovolts divided by root 3 angle 0 degrees volts. VAN. So this formula is very important and we will use it a lot. In just the question says 500 kilovolt, or the example says, or the problem statement 500 kilovolts. Then from that word and 3-phase 500, I can find V line to line, V line to neutral, VAN directly. Just by reading only this statement. A 3-phase system has 500 kilovolts voltage. Then from this information, you need to do this procedure. So you will see that this procedure, we will use it a lot. These 3. We will use it starting from now until the end of the course. So I think we will use it more than 100 times. V line to neutral equal V line to line over root 3. Then VAN will be V line to line angle 0. Then what else? If you see in the problem statements that the voltage is V line to line or voltage is V line to neutral, use what you have in the problem statements. If there is no indication, again, this is line to line. The other thing, if you don't see any information about the sequence, then the default is positive sequence. If you see any problem statement, if it says, assume this system is negative sequence, then use the negative sequence. Assume this is positive sequence, use what you have. While if the problem statement, no indication at all, the default for any system to be positive sequence. So keep in mind, if there's no information about the sequence, positive sequence. It looks like, let's recall back when we discussed about AC circuits, we used to say, if there is no indication or no information about the frequency, assume it's 60 Hertz, right? Then the same thing here. If there is no information about the sequence, assume it positive sequence. Then the last thing about the assumptions, the power always given as three-phase quantity. Okay? So what does this mean? We will discuss the power later, but just the power, complex power for the three-phase, or if there is no information about the complex power, this is the total complex power for phase A, phase B, phase C. So if, for example, we read from the data sheets a 100 kilowatts generator, then you will know that this 100 kilowatt generator is associated with the three-phase, with phase A plus phase B plus phase C. So if you need to find it for a single phase, if it is balanced, you will say 100 divided by 3. If it is unbalanced, you need to calculate for each phase alone. Then again, these assumptions are always true unless you've been told in the problem something different. So the default for any system or any voltage given is line to line, unless you see it's line to neutral given, it's told you it's line to neutral. The default is three-phase quantity powered or positive sequence, unless you've been told something else. Any questions? Okay, good. Now before going to the other Y connection, I would like to give you an example about the three-phase analysis. So assume we have the following information. So here is an example. We have VAN given as 120 angle 0 degrees. VBN equals to 118 angle negative 110 degrees. VCN bar equal to 122 angle 130 degrees. Okay? So the first thing, is it balanced? Then the second thing, which is, what is the approximated sequence? Since it asks me about the sequence, I'm not going to assume the sequence is positive or negative. I need to know, because it's given. It's given some information, so we need to do some calculations. The third thing, which is find line-to-line voltages. Okay. Actually, that was that example was quiz plus last. I did a quiz like this. So the first thing, or the first question, is it balanced? And of course, we need to justify. Not only say balanced or unbalanced, but you need to justify it. So let's start with the first one. Before saying is it balanced or not, what do we know about the balanced system? We need to have three conditions. First condition, same magnitudes. Second condition, same loads. Third condition, phase shift 120 degrees, right? Then here, there is no information about the loads. The only thing that we have is to check the magnitudes and the angle, right? Now, are those sharing the same magnitude? No. Therefore, definitely is unbalanced, right? Okay. If, for instance, let's assume if they are sharing the same magnitude, look at the angle. Are those, do they have the phase shift 120 degrees? 0 and 110, no. 110 and 130, 130 and 0. So no, they are not sharing this 120 degrees. So you need to make sure all of these three share 120 degrees when you do the subtraction. So they are not. Therefore, we will say it is unbalanced. And unbalanced for two reasons. The first reason, in magnitude, it's different. The second reason, phase shifts. It's not 120 degrees. So, problem number one, done. It's not 100 degrees. Problem number two, what's the approximated sequence? So the sequence, we used to know positive sequence, negative sequence. As a summary, to just memorize, positive sequence ABC, negative sequence ACB. So this is the positive, this is the negative. So ACB used to be with angle A 0, B negative 120, C positive 120. ACB 0, negative 120, positive 120. Now let's compare and see. VA with 0. We have VA with 0. VB negative 120, C 130. What's the closest value? Is it ABC or ACB? So negative 120 with B, C with 130. So ABC, right? So it's close to ABC. Therefore, we will say it is positive sequence. And again, it's the approximated because it's not 100% positive sequence, but it's close to it. So positive sequence, or in other words, you can say either positive or ABC sequence. Both of them are correct. Okay? Now, number 3, which is we need to calculate line-to-line voltages. V line-to-line voltages. Line-to-line, again, we need to calculate it, all of them as VAB, VBC, VCA. So again, it's not like exactly V line-to-line, it's line-to-line voltages. Line-to-line. VAB, VBC, VCA. How can we calculate this? Okay, in the notes. Let's go with it. So here in the notes, there are formulas. Our sequence is positive, so, right? So we will say VAB equal root 3 angle 30 times VAN.
But it's unbalanced.
Excellent. It's unbalanced. Let's go back here. We said these formulas are not always true. If the system is unbalanced, don't use this, right? So we cannot use this. Even though that we say, okay, the system is positive sequence, but we cannot use them. Therefore, when we say VAB equals square root 3 angle 30 degrees times VAN, this is not true because it is unbalanced. What should I do? Use the general formula. So how to calculate VAB, VBC, VCA? We can say VAB equals VAN minus VBN. So VAN is actually 120 angle 0 minus 118 angle negative 110. I encourage you, when you put this in the calculator, put a bracket for each number. VBC equals VBN minus VCN, which is 118 angle negative 110 degrees minus 122 angle 130 degrees. Then the last one, VCA equals VCN minus VAN. Then it will be 122 angle 130 degrees minus 120 angle 0 degrees. Actually, I don't have the numbers, but that's how we find it. Just you can use the calculator to do it. That's the only way. We cannot use the other formulas. Keep in mind, if we need to use the other formulas, we need to have a balance system. Okay? Any question? Now, one more thing, which is related to the three-phase system. So now we know we know there are 6 voltages, 4 currents. And let's recall last lecture when I told you about the introduction of three-phase system. I mentioned that the three-phase is based on 3 conductors, which is A, B, C, and neutral, right? That's what we used to do. And we say there is IA, IB, IC, then we have I neutral, right? That's what we said. Then we said also IN neutral equal IA, IA plus IB plus IC, and we used to say it will be 0 if and only if it is balanced. Is this correct? That's what we discussed. Now let's assume we can guarantee the system is balanced. The neutral current will be 0, right? So what's the point of adding the neutral if it is 0? Can we eliminate the neutral? If we eliminate it, we will save more money, right? So the question is, can we do A, B, C alone? Yes, we can. Yes, we can. But keep in mind, we need to make sure it will be balanced to avoid problems. With this situation, if it will be unbalanced, this will cause some problems, especially for the utility power lines. We don't like it. How we can make sure? We need to make it balanced. Okay. How can I guarantee this will be balanced? This is actually depending on, and we need to go a little bit to that image, to the power lines. Here. Now we need to transmit the power lines from the source to where the loads. Okay? When you transmit the power, we will see, where is the pin? There should be a pin here, I don't know. I mean, when you go to the power lines, you will see this area is called transmission, and there's area that supplies to your home. Supplies to home or industrial loads, right? So we have 2 areas. With the high voltages area, whereas we use a very large towers, for example, transmitting the power for 100 miles or 200 miles, it will go from one station to other station. In the middle, there will not be any loads. It will go from point A to point B. So, since it will not go, I can guarantee from phase A or from point A to point B, they are all will be balanced because there is no load connected, right? Then when we transmit the power, why do we need to add a neutral? We don't need. We can remove the neutral wire and transmit the power for high voltages or extra high voltages or even medium voltages as only A, B, C without a neutral. And that's what's happening in real life. We can save more money by avoiding using the neutral. Because transmitting the power from A to B without any disconnection for 100 miles, 200 miles, then I can save more money by removing one conductor. That's one way. That's one advantage, right? There is something else which is saving the money. Now let's look at the distribution area when we connect this to the loads and the home. When we go to the distribution area, basically most likely I'm talking about low voltages. When you connect this through the power lines or the transformer or whatever we have, then the load will be supplying your home, supplying your neighbor home, supplying other part of home. So we have, for example, 3 or whatever neighborhood. So we cannot guarantee your home, which is connected in phase A, is the same load consumption as your neighbor home B or your other neighbor home C, right? So we cannot guarantee the system will be balanced. Even though we can try our best to try to equalize, balance the load, but we cannot guarantee 100% to be balanced. So it will be slightly unbalanced. This slightly unbalanced, if there is no neutral, this will cause a lot of problems, especially in the power lines. How we can avoid these problems? We need to add the neutral. So definitely, when we have in distribution area, the neutral is requested, or it is a must. Whereas, where I can get some scenarios, it might be unbalanced, then I need to have the neutral. So in other words, I will say we will use the neutral system most likely for distribution area, while we will avoid using the neutral when we are in transmission. And actually, the transmission is cost way much higher than the distribution, especially with regard to the neutral, because in the distribution, basically it will go for few miles. For example, inside Auburn, look at the closest substation here, electrical substation, which is we have it close to the stadium, and it's not too far. Or we have, for example, one at Dean Road, or we have one at Sanford, whatever. So we have multiple here, and it will go for a few miles at max. It will not go for very large stations. So as a result, we can put a neutral without any problems. While when we are in transmission lines, transmitting the power, for example, from Lagrange to here, it's, I don't know how many miles, but it's long distance, or from Birmingham to here, whatever, then it will be very long distance. So when we remove the fourth wire, this will save a lot of money. And even like the neutral, it will be meaningless because it's zero. Okay, does this make sense? Now, I discussed about the power lines. Okay, how is the sources or the loads connection will be? Okay, so I said like there are 4 lines or 3 conductors. How the sources will look like? Okay, I'm gonna write also here introduction, then we'll go to the notes. So for the sources, again, we have 4 wires, 4 conductors. We can have a source is called Y connection. Basically, there will be 3 sources. So here is voltage source, here is voltage source, here is voltage source, and the returning current for the neutral. And to the load, we have the same thing, Y, which is here's an impedance, impedance, impedance for each phase. Then this is called Y or star connection. How is called Y or star? Basically, I can remodel this or rewrite this to be as Y shape. Okay? So the top and the bottom are exactly the same. But just like I make the shape, it looks like Y. So this is called Y, or it's called star sometimes. It looks like a star or it looks like a Y connection. Some textbooks call it Y, some textbooks call it a star. So this is the connection for the source. And how many conductors we have? 1, 2, 3, 4. So star connection or Y connection can be used for a balanced situation. Now, if we have 3 wires, not 4, how is the connection will be? When we have only 3 wires. So for 4 wires, every time must be with Y. 3 wires, we can have actually 2 connections. The first connection, here is a source, here is a source, here is a source, and here is a load, here is a load, here is a load. So this connection is Y connection as well. So here is, in other words, it will look like this. Very similar to the previous one, but I'm just removing the neutral. Okay? This is still Y connection, or star. And there is other approach, other than this connection. We still have 3 wires, but what we will do is we will add a source here, source here, source here, then load here, load here, load here. Okay? So with this one, what we will have, what do we have? You will have, we can write it like this way. Like delta shape. So this shape is called delta, or in other words, delta connection. Okay? What's the difference between 3 things? We have Y, 4 wires, Y, 3 wires, delta. So I can just write here a summary. We have Y, 4 wires, we have Y, 3 wires, we have delta. So Y, 4 wires, again, we have these sources, as in look at the source, then 4 conductors. Y, 3 wires, we still have these sources, 3. Delta, like delta shape. Okay, and we have 3 wires. So delta is all even like 3 wires, it's also 3 wires. What's the difference? Here, between Y, 3 wires, Y, 4 wires, neutral exists, neutral exists. But here, I would say, the neutral exists, but no wire. With Y, 4 wires, neutral exists with wire. While the last one, neutral does not exist at all, which is delta. Neutral does not exist. And of course, no neutral wire as well. So you need to be familiar with these 3 cases. We have Y connection with 4 wires. Whenever we have 4 wires, definitely it's Y. We have 3 wires. Is the neutral exist or not? If it does not exist, then it's delta. If there is a neutral part, there is no wire, then it is Y. Okay? So again, the difference between delta and Y is the existence of the neutral. No matter if it's 3 or 4 wires. Delta, there is no neutral at all. Neutral has been eliminated and not connected at all. While delta or Y, there is a neutral. Okay, any question? Okay, so let's stop here. Next lecture, we will go to more details about delta and Y connection.